This is version 4 of the BLDC motor controller, and the main difference in this revision is a new bridge, and these are IGBTs instead of MOSFETs, and they're also paralleled with ultra-fast flyback diodes. And you can see these are the three-phase legs. 30 ohm gate resistors. This is the positive rail. This is the ground rail. My last one did okay at 18 volts, but when I stepped it up to 36 volts, the MOSFETs burned out. And I'm not exactly sure why, but I have two theories. I haven't proven either of them out yet, but the first is that the body diodes in the MOSFETs weren't fast enough, and I'm hoping that's not the case because the MOSFETs are a little more efficient at the lower voltages. My second theory, and I haven't been able to prove this, but I'm pretty sure this is what it was that I had two of these batteries strung up in series and some pretty thin wires. So I think that with the high current draw, the voltage that the batteries were supplying dropped down pretty significantly, but the 3 microfarad capacitor that was storing the charge pump voltage would have still had that high 52 volts, even though the rail voltage would have been more than 20 volts less than that. So anyway, there might have been over voltage on the MOSFET gates. The microcontroller here is an Atmel 328P, the 16 megahertz crystal on it. So this is an Arduino platform. This is basically just an Arduino on a circuit board here, and then I have it connected to an AVR programmer with a USB connection that can go into the computer for uploading new firmware. Let's see. So for power supply, I've got an 18 volt DeWalt battery. Here's the schematic. So I've got a 17 volt linear regulator, 5 volt linear regulator, and that's right here. It works, but it generates a lot of heat, so I'm going to have to figure out something better. This is the charge pump, and it's got a 555 timer and a Dixon charge pump arrangement here. And that's also in here. So this steps up the rail voltage an additional 17 or so volts, and that way I can use N-channel MOSFETs for the high side, which is pretty standard. And the charge pump also, this generates a lot of heat. That's what this, let's see, you can't really see it, but there's a big resistor right here that dissipates a lot of heat. So I've got to improve that design some, but it does work. These are op amps that are connected to a shunt resistor, although I haven't implemented that. That's just for current sensing. That's not necessary for this test. Here's the totem pole drivers. These drive the MOSFET gates, and that is kind of a mess of wires here implemented throughout there. So there's 6 sets, 3 for the high sides and 3 for the low sides. 1 high and 1 low per phase. There's 3 phases. This is a 5 kilowatt BLDC motor. It has support for liquid cooling in it. You can see where that plugs in, which is really nice. In the previous versions, I'd been using a car alternator with a permanent magnet rotor, and I still like that idea. But for the price, this thing's hard to beat. This is from Golden Motor. It has the hall sensors already built into it, and that's what these are. Here's hall 1, hall 3, hall 2, and then 5 volts and ground to power the hall sensors. This pot right here is the throttle. It's just controlling the PWM frequency of the high side. So at max, at 100% duty cycle, it's basically doing 18 volts. The carrier frequency is 16 kilohertz, and then the actual frequency is 1 kilohertz. And I have 16 integral steps in the frequency. Here's how I turn it on. Oh shoot. I forgot. I like to unplug this thing first so that the 5 volt power supply from the battery doesn't fight the USB from the computer. I had a problem with that once, and I thought I lost my computer. Okay, so here I'll adjust the throttle. This is going down. I'll throttle it back up slowly. And here's the power off. So it seems like an awful lot of work and complexity just to drive a motor, but this is kind of a trivial test case because remember, this motor is capable of doing 5 kilowatts, and this battery's only putting out, I don't know, but probably at most around 100 watts. This design with some additional power bridges could do 50 kilowatts, maybe 100 kilowatts, support regenerative braking, and the efficiency of this thing is brushless. The efficiency exceeds 90%. So this is a really great platform for an electric vehicle. So the extra complexity is worth it.